Hello, welcome, and an excellent evening. Today I want to talk a bit again about MS-DOS memory models. They are not particularly linked to MS-DOS per se, but to the compilers and runtimes that work under MS-DOS. And since we're working with Turbo C most of the time here, I want to take a look at the different memory models that Turbo C offers. The memory model can be changed by going to the compiler options and then to the model options, and basically you have 6 different models: tiny, small, medium, compact, large and huge. They have mostly to do with what kind of memory is available and how pointers are constructed by default. For example, the tiny memory model has a total of 64K for all the code, data and stack in the program. All the functions and data pointers are near by default. Tiny model programs can be converted to COM format. This is also the only thing I think that can be converted to COM format. That's why it is quite useful for those. So it's for small programs. And the difference between near and far pointers, I think we talked about in an earlier episode, but to be very quick about that, a near pointer basically means that in the code or in your memory somewhere you only store the offset, which is a 16-bit pointer, so you can only point to 64 kilobyte at a time, and it will use whatever is currently in the DS data segment register to determine where exactly in memory it is. As you remember, the 8086 and 8088 in real mode, also the 8286, 8386 and all the later processors can access 1 megabyte. And for 1 megabyte you only need 20 bits of address space, basically. However, the 8086 and all the other CPUs have 32 bits of address space, namely the 16-bit segment register, like DS or CS, plus one of the offset registers that you can use on top of that. That gives you 32 bits. So where are the 12 missing bits? Well, the segments are not like banks on other 8-bit machines, for example, like on the Commodore PET or similar things, but the segments are overlapping. So every 16 bytes, a new segment starts and it overlaps with the previous segments for most of it, basically. So that's interesting. That's also the reason why you can access in real mode the top 64 kilobyte, the high memory area, by using the very last segment and disabling the rollover to the bottom of the memory. So that's why you get 1024 kilobytes plus 64 kilobytes extra. Now this is only a small detour. Let's have a look at the next memory model. It's the small memory model, and there you have 64 kilobyte for the code and an extra 64 kilobyte for data and stack. So that means for tiny, CS and DS are equal, point to the same segment, and for small, you get 64 kilobyte for code and 64 kilobyte for data. In CS and DS, there will be different segments. All functions and data pointers are near by default. Makes sense. Medium. Here you have 1 megabyte for code, so any code pointers will be far, which it says here all functions are far by default, but only 64K for data and stack. So this is something that you would use if you have like very large program where you have coded a ton of stuff into the source code itself, but you only have few variables and runtime data. That would be the idea here. The compact model is the other way around with compared to the small memory model. It again has 64K for code and stack separately, and static data, obviously, it says here, which wasn't mentioned in the small model at all. and up to 1 megabyte for the heap. So for data that you get with malloc, all function pointers are near because you only have the 64K for code, and all the data pointers are far by default. This of course also influences how much memory is used during runtime, because if you have a lot of data pointers and they suddenly are far by default, it takes up double the space. For example, if you have linked lists or stuff like that, then it consumes more memory. And also it might influence runtime speed, because a far pointer might be more costly to decode and load data from than a near pointer, depending on the CPU generation. Then we have the large model. This model has up to 1 megabyte for code, 64K for stack and static data, and up to 1 megabyte for the heap. All functions and data pointers are far by default. So this is already pretty massive and gives you almost everything that you can get in real mode. And then there's huge model. This model allows multiple data segments, each 64K in size, up to 1 megabyte for code and 64K for stack. All functions and data pointers are assumed to be far. So the reason for this, I actually don't quite know. I think the idea here is that if you have multiple data segments, you could use near pointers in each segment, which is better for the performance, because right now we will use the small memory model for our program, and the reason for that is I want to show you that besides near and far pointers, there's also a thing called huge pointers, and there's a reason to have those. But first of all, let's see. This is an empty stub program which only determines the memory model, because when you're compiling, there will be a macro defined with the name of the memory model and 2 underscores leading and afterwards. So if we run this, it should print out memory model detected, small. Okay, so we are in the correct memory model. And what I want to do today is, so far, any data that we allocated could not be larger than 64 kilobytes. We could do a far malloc, because the regular malloc function in some memory models would only allow you to allocate at most 64 kilobytes. But on the far heap, you can also do a far malloc with an unsigned long, giving you a couple hundred kilobytes at most in DOS, because you have not more than 640 kilobytes free that you could allocate with this function. The usual malloc could do that if you're in the right memory model. But let's assume we want to be not very portable but program for DOS. Then we would use far malloc to allocate, let's say, a chunk of 128 kilobytes. Okay. The question is, how do we access the data in there? Does it work by doing square brackets and then an index, or maybe just pointer arithmetic? And what will happen? So that's what we want to find out today. So we need to add a couple of variables. First, I'm going to introduce a variable where we store how much we want to allocate. That's called nhuge. And we want also ask how much far core memory is left in the far segment. And we need an iteration variable to write to this data and to verify that it's correct. Then we will have a couple of pointers to access this. First, a far pointer, which we just call pfar, which we'll initialize to null so we don't do any stupid things, or we will notice if we do stupid things. And I will also already introduce a huge pointer, which is a little bit different, and we haven't used that before. And that's that. And we should also have a near pointer. Maybe not to this far segment because we can't do that, but we will also compare by doing a regular malloc with a near pointer. And for the near, we will also use a thing that I will call compact, which will be only 16 kilobytes or 16,000 bytes to be precise. And we'll also ask what the near core memory looks like, because that should be less than 64 kilobytes from what we learned in the online help. Also, I want to test the performance, so we will have some clock ticks for the start of our performance test and the ticks at the end of the performance test. And we will convert that to seconds, so we need a float to give a fractional value. Then we do the regular clear screen, detect the memory model. We already seen that. Now we're going to try and allocate far memory. First we will test how much memory we have left actually there. So far core left equals far core left. There's a function in, I think, alloc. Yes, far core left returns measure of unused memory in the far heap. That's nice. That's how much we can allocate. And we will print it out, I would say, so that the user knows how much memory there is. It will be different if we run it from inside Turbo C and outside, because Turbo C takes up like 200 kilobytes on its own or even more. So if a program doesn't run, if you're running inside here, just compile it, leave the IDE and run it again. There's also a command line compiler called TCC, which we haven't used yet, maybe at a different time. So we print out long unsigned bytes of far core memory left. And I think we should use a new line and then do n far core left. Does that actually run? I think it did. And it says 241,000 bytes of far core memory left. Great. So that's nice. Then we will try to allocate something. pfar equals far malloc with n, what did I call it? N huge, right? Yeah, seems like that's what we did. And we'll also convert this to a huge pointer just by assigning. That will be an implicit conversion, but you could also write something like jar huge star. This would be an explicit conversion, and that might make sense to do that. Far malloc, yes. Far malloc is a great name for a function, but it's not what we want. We assigned a lot of values that we didn't use, but I don't care right now because we will use it in time. We will test if the allocation worked. So if pfar equals null, then the allocation did not work. And then we will do a printf not enough memory. And we will quit the program because it will make no sense to continue here. Okay, then we can also do another print so that we know where we allocated this. So let's do that. We will say allocated %lu bytes at, and now we will print a pointer in far pointer format. So that is %, or let's put a 0x. Do we want a 0x? So we don't need a 0x. But we'll print a far pointer, which is capital F and then P for pointer, and then \n, and it was in huge, and pointer far. So that should do the trick. And just as a test, we will also do another update of the, actually we can copy that from up here. We will test again how much far memory is there. And that should already run. We allocated 128,000 bytes at 6582. That's the segment 0008. And after that, there's 111,000 bytes of hardcore memory left. So you see, there's not that much actually available after that. And I think I did not copy, I moved. So let's copy that back up here again. And that should be better. Yes, that's much better. Now we see before 239, afterwards 111. Great. Okay, this is looking good so far. Now let's try to write to the memory. So we'll write something like filling memory using far pointer, like so. Then we will measure this, how fast this is. Ticks start equals clock. This gives us the clock ticks since program start. And a little for loop with the iterator that we created from 0 to n huge, so 182,000 plus I, then something like this, and we will use the far pointer and we can just access it like this. This should be fine. Equals unsigned char I modulo 256, and we need to put a parenthesis around that so that we will count up all the time repeatingly from 0 to 255. This should give us a good thing that we can validate. Ticks end equals current clock, so we can measure it. And then we'll print done. And we will print out how many seconds it took. Took percent 5.3. This will give us 5 digits with a decimal point and 3 decimal digits, I would say, seconds. And a \n there as well. And then we will need to do a float conversion of ticks start, no, ticks end, of course, minus ticks start, and we'll divide the whole thing by clock tick. This is a macro that is defined in time.h. If you look at clock, it gives us back a clock t type, and you can divide this by clock tick to convert it to seconds. And there it says the clock tick constant defines the number of clock ticks per second. But you need to do the float conversion or else you will get an integer division, and that might just lead to a 0. So that's the filling of stuff. Let's run this. Filling memory using far pointer takes 0.165 seconds. Okay. That's not super fast. That's something like maybe a megabyte per second, but we are also running only at 10,000 seconds. So not super fast, but still something that you can do. Now we want to know, did we write the correct values into there? So for that, I will use the huge pointer. For a reason that will become obvious in a minute. Verifying memory. We will do another loop. the same loop we had above. Plus plus I. Braces. And then if P huge, which points to the same memory, P huge of I is not equal to this here up here, right? Because that's the value that we are expecting at this place. Then we will print failed at byte number %lu with a new line, and then it's byte number I, and we will break. We will not continue here because we already failed. And when we're done, we write done. No matter what, if it was successful or not. So let's build this and let's see what it said. Filling memory, verifying memory, failed at byte 65528. Oh, that looks pretty much near a segment boundary when the segment wraps around. Because we started at 0008 and 65528. 65528 plus 8 is 65536. Yes, that's exactly a segment boundary. So what happens if we write with the far pointer? A far pointer can point to an arbitrary place in the 1 megabyte address space of the 8086. But once you increment it, and that's what we're doing even with the square brackets and the I, if you increment it to more than 65536, it will wrap around to 0 without incrementing the segment address and wrap around to the start of the segment. So you will never address more than 64 kilobytes with a far pointer. So Turbo C introduced a huge pointer, and the huge pointer, whenever you do pointer arithmetics, it will adjust the segment address together with the offset address so that you will have a mapping. But that runs through a function which is slower than what we saw before. So let's try this. Let's try to use the huge pointer to fill the memory and do the whole thing again. So we can basically copy this whole block here. Okay. And do everything including the verification. And let's rewrite this using the huge pointer, which is here. Took something seconds, then we will do that. And now when we build this, we should see filling the memory failed, and then filling the memory using huge pointer done, took 0.44 seconds, verifying memory done. So the verify was successful at the expense of performance. Now it takes almost half a second to fill 128 kilobytes of memory. So this shows that if you have large data in quotation marks in MS-DOS real mode, for Turbo C, you can do that very easily as a programmer using huge pointers, but it will cost you runtime. It will be much slower. So if you can use near pointers because they will be the fastest, then use far pointers if you need space that is not on the near heap. And if that doesn't work out because you need even larger, either break down your algorithms to detect when you're stepping over the 64 kilobyte boundary, or delegate it to Turbo C by using huge pointers. So we did have one more thing. The near memory, that's what we wanted to look at. And we can actually copy this once more and change that to use the near memory. Filling memory using near pointer. Also allocation. And I think, I don't want to do it like that. Let's delete that. Let's go from the top because we need the allocation as well. Or let's just write it down. It's maybe easier to follow. So first we get how much core is left. This should be much less than the far core, obviously. We'll print that out. Know the drill, %lu, bytes of core memory left, or let's say near core memory left in this case, and core left. Then we will try to malloc something, and we don't do the whole 64 kilobytes because we also need something for the stack, etc. So we call this n compact. If p near equals null, then it didn't work. So we'll print not enough memory, and we'll quit. No sense in continuing. This is something you should always do because it can always happen that you're running out of memory for one reason or other. So please always check the return value of malloc. Then we say allocated %lu bytes at %fp. We will print out this as a far pointer, which doesn't matter. We just see the segment address, which is interesting, at least a little bit, to compare to the far heap so that we can see that the near and the far heap are actually different things. With the near pointer, and then we will see how much core memory is left. That should have decreased. And we can actually copy that. No need in writing this down again. And then we can start filling the memory, and I think I can actually do that by copying and verifying that I did this correctly. Filling memory using the near pointer. So we are using p compact and timing that. That's also interesting. Verifying memory using the huge pointer. Yeah, we can do that, but then we will need to do p huge equal to p compact. Otherwise it will test the other, and that will make no sense. And that is it. We should do a free p compact and far free p far, but it will also be returned at the end of the program. And we've got a couple of errors because I forgot some parentheses here. Then a warning. Undefined symbol p compact because it is probably called p near, right? Yes, it is called p near. It was n compact for some reason, which is probably not a good idea to name it n compact. So compiling, and that's the last of the errors, and everything is good. So let's run the whole program. And we got a break because I used the n far. Okay, let me repair this real quick. Yeah, here we are. We filled up using n-huge, which of course can't work. P compact, n compact. I think that's correct, right? It all. Yeah, that seemed to have worked. Okay, I should have added one more new line, but okay, that's fine. So we have 62,886 bytes of near core memory left, and we allocated 16,000 at 004B, a totally different segment compared to the far heap. And we got 468,000 bytes of near core memory left. Okay, that's fine. Then it's filling. It took 0.055. 128 divided by 16 is 8. So it is quite slow, because if we take this times 0.055, it's 0.44. So it's as slow as the huge pointer. Interesting enough. That seems to be quite slow. Let's try to allocate a little bit more. We have 62,000 left. Let's see how this works out if we crank this up from 16,000 to 60,000, let's say, because that should still fit in. Okay, this looks better. I think we're here at the resolution of the clock ticks, probably, because filling... Oh, it failed at byte 60,000. Interesting. That's quite an interesting thing to happen. But it is quite fast, which I would have assumed. But the question is, why did it fail? Because, again, we used... Yes, we verified using n-huge, which is, of course, garbage. So let's do the n compact. That's the copy and paste error again. Let's run it again. And now the verification works. Okay, everything is fine. So I think the near memory is so fast because we don't have to deal with the segment registers. We're still relatively slow using the far pointers, super slow using the huge pointers, and the near pointers are super efficient, because I think this is the maximum resolution we get from the clock ticks, that writing to 60,000 bytes is ultra quick and takes only 55 milliseconds at most, probably even less. So there you have it. Near pointers are super fast, but you can only address 64 kilobytes and only one segment. If you can't manage to switch different segments, and that's why probably the large memory model is quite nice. Or was it the huge? I think it was the huge, right? Because it has multiple data segments, each 64 kilobytes in size. Switching to such a segment and then using near pointers would be super fast. But that's something that you can't do always. So put the data that you need regularly on the near heap. That will be fast. Data that you irregularly need, for example, some initializations, or if you do a mem copy, that could also be relatively fast using far pointers. Then you could use those. And huge pointers only if you have something like, if you're coding an app, not a game, where timing doesn't really matter that much. Yeah. So there you have it. I think that's all I can say about the huge, near, and far pointers in the different memory models. All this goes down the drain once you go to protected mode, because there you don't have the distinction anymore. You can create a flat memory space where you just have 32-bit. But this only works on 286, 386 and above. And especially almost nobody uses the 286 protected mode, which is also, I think, still segmented in a way. But the 386 can produce a nice flat memory space. But that's something that only runs on 386 and above. And here we still want to target the original PC and XT and do stuff for those old machines. So coding in DOS real mode, I think, is still interesting because it has these quirks. But yeah, that's it for the moment. Leave a comment, share, like, and subscribe, the usual stuff. Again, you can find me on Mastodon over at chaos.social/@root42. You don't need to subscribe there or anything. You can just read my page and my feed. But if you join Mastodon, you can interact with me there. That's the place where I hang out the most. But also I try to respond to almost all the comments that I get on YouTube. That's it for today. Thanks very much for watching and see you in the next episode. Bye!